All right, section 6.2, sorry for the 4 or 5 second delay there. Section 6.2, we are talking about projectile motion 6.1. Now we're going to be talking about circular motion. Now circular motion, the keys with circular motion are a couple things. First things first is because the direction is always changing. Remember, even though it might be the number might be constant, since velocity is a directional directional to vectors, it's always changing direction. So if I take 4 separate spots around this circle here, if I would let go of whatever I was spinning, it would go in this direction, this direction, this direction, this direction. It'll let go. But since the direction is always changing, since it's a vector quantity, the velocity is constantly changing, so therefore the acceleration is constantly changing. Even though the number, the numerical value might be the same, the direction also makes it change. So when we talk about uniform circular motion, there's 3 equations that can help us come up with circular acceleration. And the first one here is going to be on the bottom. Velocity is equal to change in radius divided by change in time. And if we're going to take a look at that with a picture, here is object 1 in time. Here's object 2 in time. The distance between them would be the change in radius. The change in time would be how far it took to go from point A to point B. And that would calculate my velocity. That would be the first way to calculate my velocity with uniform circular motion. Now, there are 2 other equations that we can talk about when we're trying to solve for centripetal acceleration, or the acceleration of a circle going, an object going in a circle. And the first one is AC is equal to v squared divided by the radius, where AC represents our centripetal acceleration, V represents our velocity, and R is the radius of the circle, or the radius of the path of the circular motion. So that is the first one. Our second equation is going to be focused on period. And period is the amount of time it takes to make one lap or one circle revolution. So for example, if we're going to use period, capital T, the period of Earth is 365 days. It takes Earth 365 days to do one revolution around the sun. So period is the amount of time it takes to go around the circle or around its lap one time. If we have information pertaining to the period, we can do a second equation for centripetal acceleration, which is AC is equal to 4 times pi squared times r. The only divided by t squared. The only thing that is squared is the pi. So it's 4 times pi squared times r divided by t squared. So pi is squared, t is squared. Those are the only 2 factors. Pi is a given, r is the radius of your circle or your loop, and t is the amount of time it takes to finish that loop. Now if we take centripetal acceleration, we're able to figure out the force of centripetal motion or circular motion, and the net force is equal to m times a. When you're figuring out the force of an object moving in a circle, you're just using m times a, except your acceleration is going to be your centripetal acceleration. So if we take that and look at a problem, we can go ahead and do a problem dealing with centripetal acceleration. We have 2 questions to answer here. Number 1, all right, a 0.013 kilogram rubber stopper is attached. Let me get that out of the way. Sorry, guys. Is attached to a 0.93 meter length of string. The stopper is swung in a horizontal circle, completing 1 revolution in 1.18 seconds. What is the centripetal acceleration of the stopper? Question 1. And question 2, what is the force the string exerts on the stopper? Well, we go ahead and let's figure out what we have given to us in the problem. We have the mass of the rubber stopper. So our mass is 0.013 kilograms. The radius of the stopper is 0.93 meters. And it tells us that the period is 1.18 seconds. Those are our 3 pieces of information. It's asking us to solve for centripetal acceleration. we have two choices to solve for centripetal acceleration. V squared divided by r, or 4 pi squared r divided by t squared. We are given r. We are not given v, which means that our top equation is probably not going to work, and we're going to be stuck with the second equation. So if we go and write this out, we are left with AC is equal to 4 pi squared r over t squared. We go ahead and plug in our numbers. 4 times pi squared times r, 0.93, divided by t squared, 1.18 squared. Go ahead and do your math, and with sig figs, 2 sig figs, our centripetal acceleration is 26 meters per second squared. Our second question then, what is the force of the string? All right, what is the force the string exerts on the stopper? Well, remember, force is equal to mass times acceleration, or our centripetal acceleration. So if we take our force, that's equal to our mass, 0.013, times our centripetal acceleration of 26. To go and figure this out, the force being exerted with two significant figures is 0.34 newtons. So when we talk about centripetal acceleration, those are the three major equations we're going to focus on. We're going to focus on AC is equal to 4 times pi squared times r divided by t squared. We're going to focus on v squared divided by r. And occasionally, we might get the change in r divided by change in t, which will help us give velocity, which therefore can help us solve for centripetal acceleration. But that, in a nutshell, is centripetal acceleration. We're really just talking about circular motion, objects moving in a circle. Remember, when you're moving in a circle, the acceleration and the velocity is always changing, since the direction is always changing. Therefore, your acceleration is always changing. And that concludes section 6.2.